All right, in Chapter 6, we're continuing with probability, but specifically looking at random variables. And we're going to start with what's known as discrete random variables. All right, so some definitions. A random variable that takes a numerical value that describes the outcome of some chance process. That's a random variable in general. So for instance, like the number of tails when you flip a coin 10 times, or the number that you roll on a die. Things like that, the numerical values that come up, those are the random variables. Now, the distribution of a random variable, it gives you all the possible values of their probabilities. You can display a distribution just like we've done before with a dot plot and a histogram. It's just a probability distribution. So then what are some discrete random variables? All right, so here's an example. A discrete random variable is a shoe size, while a continuous random variable is foot length. Now, what's the difference? Well, shoe sizes are broken down into distinct units, 7, 7.5, 8, 8.5. Now, foot length could be 1,000 different things, a lot of different lengths going on there. Or another definition of a discrete random variable, it's a fixed set of values. And usually I talk about it as in terms of things that we count, as opposed to things that we measure, or measurements. Okay, continuous are ones that are more like measurements, and we'll get to those later in this chapter. So let's look at some examples. Okay, imagine selecting a high school student at random. Define the random variable as x is the number of languages spoken by a randomly selected student. The table below gives the probability distribution of x based on the sample of students from the U.S. Census at School database. So our table has the number of languages, 1 to 5, and then the probability that a student speaks that number of languages based on this sample. Okay? So the first thing it says is, show that the probability distribution for x is legitimate. Now, the process of doing this has not changed. It's exactly what we've done before. So all the probabilities are between 0 and 1. That's the first criteria. So that works out in this problem. The second criteria is that all these probabilities have to add up to equal exactly 1. And they do. So that's what I need to check for if the distribution is legit. Now, B says, make a histogram of the probability distribution that you see. So here I've drawn me a histogram. I want to point out a few things. X-axis is the outcomes, the number of languages. My y-axis is the probabilities. I did go from 0 to 1 on this, but I really didn't have to. If you look at the probabilities, the highest one that it had was 0.63. So I could have scaled this up to 0.7 and been fine. But notice my y-axis is decimals because it's probability values. And then I draw the histograms based on those the bars of my histogram based on the probabilities in my table. So that's the construction part of my histogram. Now, describing what you see, anytime you see that, you've got to do shape, center, and spread. So first of all, shape. We would say the histogram is strongly skewed to the right. The center, because it's skewed, we would have to use the center of median instead of mean. So the median is probably 1, meaning more than half are in 1. But the mean is going to be slightly higher because it is skewed. And then lastly, the spread. The number of languages varies from 1 to 5, but nearly all the students speak just 1 or 2 languages, so there are no outliers. Now, I will say, in my example here, I didn't give any context in shape or in center, and I should have. I did give context in spread, so that's more of the pattern you need to follow as far as bringing in the number of languages spoken by students. All right? Okay, so the same question, this is just part C. And it says, what's the probability that a randomly selected student speaks at least 3 languages? At least 3 means 3, 4, or 5, right? So I would write it this way, with at greater than or equals to, because that's at least 3. And the way I would find it is I would add up the probabilities of 3, 4, and 5. So that's what I'm going to do. So I take those probabilities straight from my table and add them up. I get 0.075. Now the next part of it says, what about more than 3? Well, more than 3 does not include 3. That means I have to do 4 or 5. Okay, so I really just have to add up those two probabilities and find my answer. Notice that the symbol here of greater than and greater than or equal to do create different answers. And that's a feature of discrete random variables. It will be different probabilities with the different inequalities. All right, so just make a mental note of that and make sure you're including or excluding the appropriate numbers. Okay, so look at our next example about roulette tables. One wager players can make in a roulette table is called a corner bet. To make this bet, a player places his chips on the intersection of the 4 numbered squares on the roulette table. If one of these numbers comes up on the wheel and the player bet $1, the player gets his dollar back plus 8 more. Otherwise, the casino keeps the original $1 bet. So if X is equal to the net gain from a single $1 corner bet, the probability outcomes are X is -1, meaning they lost their dollar, or they profited $8. Okay? Now, based on the spaces on a roulette table, the probabilities of those two things happening are 34 out of 38, and then to win would be 4 out of 38 because you're at a corner, 4 corners. Now, if a player were to make this bet over and over, what would be the player's average gain? All right, so here's how you're going to find the averages in a probability distribution. Basically, you want to add up all potential outcomes, okay, and then divide it by the total number of outcomes. So I have -1, and I need to have it 34 times because that's its probability. And then I need to add 8 4 times. So that's what this first fraction is showing you. I could simplify it and put it this way. 34 times -1 plus 4 times 8 divided by 38. Or I can do it this way. Rearrange a little bit, -1 times 34 over 38, and 8 times 4 over 38. And that's the easiest way to think about it. If you think about multiplying down the table, and then you add the results. So you don't multiply down and you add. When I do that, I get a -0.05 cents. So what does that say? If a player were to make this $1 bet over and over, on average, they would lose 5 cents. Okay, so how do you calculate mean or expected values of a discrete random variable? This is the general formula of what we just did. It looks like this. The mean of X equals the expected value of X. It's the sum of each outcome times its probability. So in that example, we had 2 outcomes, a win or a lose, and then multiplied by its probability. And we just added those 2 values up. Okay? This is something they call the expected value, and so make sure you're aware that mean and expected value really mean the same thing when it comes to probabilities. Now, second question, is it on the formula sheet? Yes, it is. It is on your formula chart. Now, how do you interpret an expected value of a discrete random variable? So from the roulette example, it says if a player makes $1 bets many, many times, the average loss would be 50 cents per bet. So notice I don't put negative on this. I just say I include the negative in words as calling it a loss. If it was positive, I would say a gain would be whatever. Okay, so be careful about that. Now, key things to remember when you're interpreting an expected value. Make sure you include something about many repetitions or many trials. And you want to say the average loss or estimated loss or approximate loss. It's not exact. So you need to include one of these words, right? Okay, so we're going to go back to the languages example we did earlier and calculate and interpret the mean of the random variable X that we talked about before. So here's the same table. So to calculate mean, we said before, was to multiply down 1 times this, 2 times this, 3 times this, all the way down, and then add the individual products up, okay? So it would look like this. This is the work you could show. 1 times that probability, 2 times its probability, 3 times its, 4 and 5. When I put it all in and I add it up, I get 1.57. So if I interpret this, I would say, if we were to select many U.S. high school students, the average number of languages spoken is approximately 1.57 languages. 1.457 languages. Now, does the expected value of a random variable have to equal one of the possible ones? Because some of you may be going, wait a minute, you can't speak 1.457 languages. That's not one of our options, okay? Because this is an average, it does not have to fit one of these outcomes, all right? So you may be saying, do I round this to 1 or 2? Don't round it, okay? The expected value is a mean, so it does not have to be a possible value in the distribution. So resist the urge to round the expected values to whole numbers. Don't do it. Normally we expect them to be decimal values because it's an average.